Chapter 3 is on solving systems of equations. There are multiple ways you can solve a system. Do you remember what a system is, first of all? Let's think back. In Algebra 1, not really, before Algebra 1, you learned how to solve an equation, right? How many variables do we have here? How many variables? 1. This is x, right? You can solve this equation. Subtract 1, divide by 2, we would know that x would be 2. Right? Can we solve? What if I gave you this equation? Could you solve that equation and tell me what x and y equal?
Yeah.
How? Okay, that would give you your intercepts. That would be graphing it. I want to know, could you solve and tell me what order pairs or solutions?
No.
Not really, we can't. Why? What's the reason why we can't solve?
Two variables.
There's 2 variables. Now, we could solve if we had another equation. We could solve if we had another equation. You could do substitution. That's one that we did learn. So if you just have one variable, you can solve, right? But if you have 2 variables, what are you going to need to solve? 2 equations. 2 equations. And that's what a system of equation is when you've got 2 equations with the same variables. In chapter 3, there's going to be 3 ways that we learn to solve systems. Number 1 is graphing. That's what we're going to do first. The second way to solve is using elimination. And we'll also learn about substitution. We did those all 3. I know if you had me, we did them in Algebra 1. So you should remember those. On the top of your paper, on the front side, there are 4 definitions that we need to write down. When we solve a system, there are 4 classifications that we can give our solutions. The first classification is consistent. If a system is consistent, it has at least one solution. If it is inconsistent, it has no solutions. If it's independent, it has exactly one solution. And if it's dependent, it has infinite solutions. Systems of equations today to find our solutions, and then we're going to classify them based on these 4 classifications. Look at the first example, example 1, please. In order to graph these, I feel like the easiest way is to put them in a slope-intercept form. You could use the cover method, but that doesn't always give you an exact graph because your points may vary off just a little bit. You only have 2 points on your line. But if you can put it in slope-intercept form, you're going to be able to extend your slope up and down and going to give you some better points to use. So let's put each of these equations into slope-intercept form. In the first equation, I might subtract x from both sides. So if y equals negative x plus 2. To graph this, we know our y-intercept is at positive 2. Put it out at 2 on our y-axis. Our slope is negative 1. Remember, our slope is really a fraction, negative 1 over 1. So I would go down 1 and right 1, down 1 and right 1. Now I am going to go up 1 and left 1 also. I'm going to extend my slope as far as I can. In either direction. And I do that so that I'm going to get an exact graph. I can figure out exactly where these lines intersect. If I'm off just a little bit, that's when I throw everything off. Take your straight edge if you haven't already done so and draw your line through those points. So graph the first equation. Now I want to graph the second equation. To do that, I would subtract x from both sides. So negative 3y equals negative x minus 6. Divide everything by a negative 3. Y equals, I have a negative 1 divided by a negative 3, which is going to be a positive 1/3 x. Negative 6 divided by negative 3 is a positive 2. So we have a y-intercept of positive 2. What do you notice about that point right there? It's the same point, so we already know our intersection point, don't we? Go ahead and use your slope to rise 1 and run 3. Rise 1 and run 3. Could have went down 1 and left 3 also. So I graphed. So what's our solution?
0, 2.
How do you know that?
Because that's where that intersect.
Okay, that's the intercept. I'll write that down. 0, 2. If an ordered pair is a solution, what does that mean? Plugs into the equation. It works when we plug it in. So you're saying if I was to put 0 in for x in both equations, and 2 in for y in both equations, that'll work for both of them?
Yeah.
Let's check. For this first time, I want to do that. I want to plug in that ordered pair. 0 for x and 2 for y. So to use the first equation, I have 0 plus 2 equals 2. Is that true?
Yeah.
So it works in the first equation. I'm going to put a check mark to show that it worked out, it checked out. Put 0, 2 into the second equation. 0 minus 3 times 2 equals negative 6. Is that true? Negative 3 times 2 is negative 6. It works. That is the only ordered pair. There's only one that makes both equations true, and that's 0, 2. There's only one place where these two graphs intersect, and that's at 0, 2. And that's what we're trying to find. That point that makes both equations true is also the point of intersection. They have in common. Let's go ahead and classify this system. We had 4 classifications that we can use. Is this system consistent? Does it have at least one solution? Yes, so we would say it is consistent. Is it inconsistent? No solutions? No. We of course have a solution. Is it independent? Exactly one solution. Yeah, we have one solution, don't we? 0, 2. It is independent. Is it dependent? Infinite solutions. It's not. Let's go to example 2. Again, let's put our equations into slope-intercept form to graph. Subtract x. So negative 2y equals negative x. Divide by negative 2. Y equals, a negative divided by negative is a positive, so we have positive 1/2 x. Now I don't have a y-intercept. Is it okay if I go ahead and say plus 0? Yeah, if you feel more comfortable having a placeholder for that y-intercept, go ahead and put plus 0 in there. So plot your y-intercept at 0. Slope is 1/2, rise 1 and run 2. Could also go down 1 and left 2. And draw in the line that goes through these points. Like I said earlier, I like to extend my slope as far out as I can. Give me a very detailed graph. For the second equation, I'll subtract x. Y equals negative x plus 6. Y-intercept at 6. Slope of negative 1. Go down 1 and right 1 until your lines intersect. That should be sufficient. So we've graphed. What do we need to make sure we do? find a point. Your graph is part of your answer, but I do need you to state the actual point that they intersect. And these two lines intersect where? 4, 2. 4, comma 2. Remember, it's a point. It's written as an ordered pair. Let's classify this. Is it consistent? At least one solution? Yes. Is it inconsistent? No solutions.
No.
No. Is it independent? Exactly one solution.
Yes.
Yes.
So it's either gonna be one or the other for consistent and inconsistent and independent and independent.
Likely. Except what if you have no solutions? It would just be inconsistent, wouldn't it? And of course, it's not independent. We don't have independent solutions. Flip over to the back side if you would. I'm going to skip that last example on the front. Go to example 4. All right, let's put it in self-intercept form. Subtract 15x. So negative 6y equals negative 15x. Divide by negative 6. Y equals, we have negative 15 divided by negative 6 is a positive 15, 6. I am going to go ahead and simplify at the same time. 3 goes into 15 5 times, and 3 goes into 6 twice. So y equals 5 halves x. Again, I don't have the y-intercept present, so I could add it in as plus 0 if you want to use it as a placeholder. So the y-intercept is 0, put a dot there. We could rise 5, 1, 2, 3, 4, 5, and run 2. Rise 5, and run 2. Put in went down 5, and left 2. I think it's really important that you guys use some type of a straight edge when you're graphing. Use as many points as you can on your line when you're graphing just to get a more precise graph. For the second equation, I would subtract 5x. So negative 2y equals negative 5x plus 10. Divide by negative 2. Y equals a negative 5 divided by negative 2, which is a positive 5 halves x. 10 divided by negative 2 is negative 5. Y-intercept of negative 5. Before I go ahead and graph any more of this, do you notice anything about the two equations? How do we know they're parallel? Good. They have the same slope, so they definitely should be parallel when we graph. Go down 5, right 2. Go up 5, excuse me, down 5 and left 2 is what it went there. Up 5 and right 2. They did have the same slope, which should have been parallel, and they are when we graph them. So if your solution is where the two lines intersect, and they never intersect, no solution. So you need to state no solution. I'm looking for you to tell me the actual point where they intersect. If there isn't a point, we would just say no solution. You could either write out no solution or use the symbol for no solution. Either one.
Oh, we put
Well, let's classify what.
inconsistent.
Is it consistent? At least one solution? No. Is it inconsistent? No. Is it independent? Exactly one. Is it dependent? Infinite? It would just be inconsistent. When it's no solution, two parallel lines, we would say it's inconsistent. So that means that these equations don't share an ordered pair. There is no ordered pair that works for both equations. Look at example number 5, please. Let's go ahead and graph each one. Subtract 9x. So negative 6y equals negative 9x minus 6.
Do we already do like divide by 3 or
Yeah, I think we already simplified.
Absolutely. Did you guys recognize that the first equation could have been divided by 3?
And then the second equation.
Yep, you could have done that also. You could have divided the second one by 2. That's a good way to start to simplify. Not a problem. You could have definitely done that. I've already started this way, so I'm going to go ahead and finish this. Negative 9 divided by negative 6 is going to be a positive 3/2 x. Negative 6 divided by negative 6 is a positive 1. I have a y-intercept of 1, and I have a slope of 3/2. So rise 3 and run 2. For the second equation, we'll subtract 6x from negative 4y equals negative 6x minus 4. Divide everything by a negative 4. Y equals negative divided by negative can be a positive, and 6 divided by 4 is really 3/2. X, negative 4 divided by negative 4 is 1. You notice anything about these two equations?
It's the same.
Exactly the same, aren't they? They're not close, they're exactly. So if I was to graph my purple equation, is it going to be any different than my green equation? No, it's the exact same thing, so I'm going to graph it twice. So think of it as you graph this green line, and I could graph the purple line right on top of it. So when we do that, where are our solutions?
all solution.
Everywhere. Don't they have every single point along the green line is the same solution as every point on the purple line, isn't it?
Yes.
So what do we say our answer is?
All solutions.
Infinite solutions. You can either write out the word infinite or use the infinity symbol.
Do we have to write out solutions or can we just write
Yeah, go ahead and write infinite solutions. Is this consistent at least one solution? Yes. Is it inconsistent?
No.
No. Is it independent? No. Is it dependent?
Yes.
Yes. So we're solving and we're classifying. That's the only thing we're worried about today. You guys are not going to have any homework over the weekend. On Monday in class, we are going to be graphing systems, so come prepared. Also bring your note sheet with you. I'm probably going to go over a couple problems again just to kind of get back into your things. It will be a Monday, have a few days off. So bring your note sheet with you. There is no homework over the weekend. If you would like to see your grade on the test, I can show you. Come on up. Not your grade, but your overall grade.